Okay, so what we're going to go over today is vectors and linear combinations. So let's start off with a couple ways that vectors can be written. Some of y'all will be used to the normal format of V, which is going to equal V1, V2, like that. Or you can write it as a column vector. V1, V2. Okay. Sometimes column vectors are a little bit easier to deal with, and especially when we're talking about matrix operations, okay? Because we're going to have matrices act upon vectors. And if you write it like this, it's not in the type of format that is compatible with matrices. So that's why we're going to be using column vectors, okay? So when it comes to addition, okay? So if we have V plus W, which would equal, this would say V1, V2, and then plus another vector, call this W1 and W2, and they have to be the same size, okay? All right, that's going to be V1 plus W1, and V2 plus W2. Okay. All right. And we also have, well, if we have C being a constant, okay. And so if we said C times V, which would equal C multiplied by V1 and V2, well, you're going to distribute that C onto both of these. This is going to equal, now C V1 and C V2. All right. And I'm just going to go ahead and we'll include the dot product. I'm going to spend more time later on talking about the dot product, but as long as we're talking about the simple properties that are associated with vectors, how would we end up multiplying two vectors together, okay? And so the concept of multiplication, so that's addition, that's multiplication by a constant, and then we have something called the dot product. Okay. Now, if I have V dot W, that's going to equal V1, V2. Okay. Now, dotted with W1 and W2. Okay. So, that's going to equal V1, W1 plus V2, W2. So that's some of the basics in regards to vectors. We're going to spend a lot more time talking about this dot product a little bit later, because the dot product also defines what length is in the normal Euclidean sense. Okay? All right. And so, all right, so to just to quote Despicable Me. So what is a vector? So Vectors have direction and magnitude. Okay. So if we define vectors in different ways, well, let's say we just did it like this. Okay, so we're going to go up 1, 2, and 3, and then we're going to go up by 1, so this is 1, this is 3. Okay, so this B right here would equal 3, 1. Oh, it's a little crooked, but I guess y'all get the idea. Okay, so this is a vector that's stuck on the origin. So what if I talk about a vector out in space? I mean, that's how we create vector fields. So a vector out in space, let's say, let's go down a little bit more. Okay, so 1, 1, 2. Okay, so let's say P1 equals 1, 2. All right, so this is the initial point. Okay, so I'm going to go up 2, 3, and 4, then 1, 2, and 3. All right, and now P2, which is going to equal 1. All right, and so we'll call this guy the terminal point. Okay, now whenever you do this, it's going to be the terminal point minus the initial point. So this vector P1, P2, let's put a little arrow on it. Okay, it's going to be the vector, okay, so that's going to be 4 minus 1, comma, 3 minus 2. So 4 minus 1 is 3, 3 minus 2 is 1. And let's write it as a column vector to show that they really are the same thing. And so that's 3, and that's 1. See now, both of these are the, well, say parallel. It's the same vector, 3, 1, but this one's out in space, and that one's just the generic one that is attached to the origin. Okay? Okay, so now let's talk about adding vectors. Okay, so let's say 1 and 2. And we're going to find W be 0, and 2. So 0 in the x direction and up by 2 in the y direction, okay? All right, so now I'm going to go up 1, 2, and 3, and we're going to go up by 1. Okay, so I'm going to define V to be 3 and 1. Okay, now V plus W. So that's going to be 3 and 1. So it's 0 and 2. And that becomes, well, 3 plus 0 and 1 plus 2. Would equal the vector 3, 3. But what is the geometry that is going to be associated with this thing? Well, what you're going to do is you're going to draw a parallelogram. So this is the parallelogram rule, right? And so if I went up, 1 and 2 straight up, and then I'm going to draw that parallel vector down there, and that's going to be the vector V plus W. Okay, so we're using parallelograms. Okay. But what about V minus W? So, you have 3, 1, subtracting 0 and 2, so that becomes 3 minus 0 and 1 minus 2. Three and 1 minus 2 is -1. Okay. Now, some of y'all might have, from high school or some of the places, might have seen some of the rules on, God, I can never remember, on tip to tail or something like that. Just draw another parallelogram. This is what's good about the parallelogram trick. But what we're going to do is we're going to flip W to be negative. Okay? So for this guy right here, so this is W. If I go down 1 and 2, this would be negative W, pointing in the opposite direction. Okay? And then V is still going to go up 1, 2, and 3. And this is still V. V is going to stay positive. All right, so let's draw another parallelogram. Okay? So, this guy would just go down by 2, and this guy is going to be parallel. Okay? So this would become V minus W. And that should make sense because it's going over by 3 and down by 1. Okay, let's say, what if we wanted to add up other names? So, we're going to draw axis on this one. But let's say we had, let's call this V. Let's call this W. Okay. And let's call this one S. And let's say we are looking for S plus W plus 2D. That's a D, not a Y. Okay. All right, well, the way you do something like this is you want to break it up into pieces. So let's do S plus W first. So let's draw a parallelogram for S plus W. Okay, so that would be S plus W. Okay, and now we're going to take V and we're going to stretch it. Okay? So I'm going to double up on the length of V. So that would be 2V. Okay. Parallel to each other. All right. So another parallelogram. And this would be S plus W plus 2D.